All right. Welcome, everyone. Thank you so much for joining us. As always, we'll just take a few minutes at the beginning, just while we're waiting for everybody to join. So, as always, with these seminars, we will be having a presentation to begin with. If you have any questions during the presentations, please do ask them in the Q&A sort of section. And then we'll have a dedicated Q&A part of the session right towards the very end, but I will monitor the Q&A sort of throughout. So if there are any questions that are sort of particularly relevant to what's on the screen, I will try my best to get those answered sort of as we're going along. So do please feel free to ask questions throughout. I just wanted to thank you all for coming along to these sessions for the last 6 weeks now. It's been it's kind of flown by very quickly. So this week we have the last two seminars of the series. So we've got this one today, which is sort of, I guess, the sort of official final one. But also because we had to cancel a session a few weeks ago, we'll be running that on Thursday this week instead. Don't worry if you can't make it. As with all of these sessions, it'll be recorded. So if you can't make it, you'll be able to watch the recording. And then next week, we'll have an admissions talk. So in our usual sort of Tuesday evening slot, we'll have an admissions talk followed by a student sort of Q&A on sort of student life and what Cambridge is like more generally. So, while we're still waiting for some people to join, I will launch the starter poll. It's super quick. So if you want to just put your answers in really quickly, and then we'll get going with the session. So the questions are, how many of the seminars have you watched, either online or in person? This is just for my own interest. I'd just be interested to hear from everybody. And then another question, which is, are you planning to attend the seminar this coming Thursday? Again, I'm just quite interested to see the answer to this. And then finally, there's a question on if you did come along to last week's seminar or if you watched the recording of it, what was the most interesting thing that you learned during that session? So I'll give everyone maybe just 30 more seconds on that because I've already done a lot of talking. I've realized I've already eaten up quite a few minutes. So I'll just give you 30 more seconds. So try and submit the poll as soon as you can. Thank you so much to everyone who has already done so. Great. So it looks like about 50% of you have attended or watched the recording of every single seminar, which is amazing. Well done. We've had quite a lot of them this year, so that's good going. And for those of you who have seen four out of five, that's very impressive as well. Most of you saying that you'll be able to come along on Thursday, which is great. I'm very pleased to hear it. Thank you for everyone who has responded. I am going to close the poll now just so that we can get moving with the session. Thank you so much for filling that in. And without further ado, I'll hand over to our speaker for today's session. So you're just on mute.
Yeah, sorry. Yeah. Thank you, Aga. So, yeah, my name is Chen Hui, and I'm a first year PhD here at Cambridge. And I do research on using hardware resources and mechanisms to provide memory safety for software systems. And so for today's seminar, we'll be like starting from a broader idea on computer security and what vulnerabilities there are like inside our software systems. And on the other hand, we'll be discussing like what the hardware and software interfaces and finally how it contributes to better computer security. And along the way, we'll slowly uncover the idea of this very brief like phrase, hardware assisted memory safety. So let's get started. And to get you start thinking, So can you give like some examples of real life cyber attacks? Okay, sorry.
Yeah, so I've just launched that poll, so you should be able to see it. So yeah, thinking about any examples that you can think of. So this could be something that you've seen in the news. It could be like a technique um, of like cyber attack or like a type of cyber attack. So whatever you can think of, please do, yeah, write your answer down and then we'll have a quick look through them. So probably give you another minute on this. So yeah, do have a think, and then we'll have a look at the answers after that. So yeah, thank you to everybody who has already given their answer. About half of you have already given their answer, which is great. Um, Probably be closing the poll in about 30 seconds for everybody else. Amazing. Yeah. So most of you have submitted. I'll just give everyone a final 10 seconds if you're still finishing typing. There was a question in the Q&A that I just wanted to answer really quickly. So somebody asked, is this the last session? And yeah, apologies, my wording at the very start might have been a little bit confusing. Um, this is this was supposed to be the last session. However, because we cancelled the seminar a few weeks ago, the actual last seminar will be on Thursday. So this Thursday coming, starting at 5, ending at 6, and then next week we have a slightly different session, which is an admissions talk. Thank you so much for everyone who's submitted an answer. I'm just closing the poll now, and I'll just have a quick look at the answers. Um, Amazing. We've got loads of really good answers. We've got WannaCry, ransomware. We've got NHS cyber attacks on here. We've got DOS/DDoS attacks. Lots of you have heard of the WannaCry attack. Phishing, Trojan horse, brute force attacks, um, malware. Loads of loads of different answers. Yeah. Ransomware. Amazing. That's really, really good work. All right.
Wow, that's actually amazing. So, I'm quite shocked that many of you knows WannaCry. So yeah, so that's a very famous like memory safety vulnerability there. So yeah, so for this slide, I have given you like a number of like common attacks that you might be familiar with. So a number of you have mentioned email phishing, distributed denial of service attack, and malware viruses. So yeah, amazing. I think probably like from the news you might have already like get into contact a lot where a number of like different forms of attack. So probably I think you might be thinking that well, there are so many forms of attack, and cyber attacks is so dynamic. Probably you won't expect or defend against like future ones. So and new ways of exploitation are emerging every day. But what if I tell you that so these are all well the forms of attack that can be fall under this term attack vectors, and the attack vectors they are actually rely on like the underlying vulnerabilities inside our software systems. While attack vectors might be very diverse, dynamic, but vulnerabilities existing in our software are much more easier to categorize. So to give you some formal definitions, attack vectors, they are specific methods used by attackers to undermine your software system. And vulnerabilities, they are flaws existing in your software systems that could exist from the conception of your system design or during the implementation or even maintenance. And well, so vulnerabilities are much easier to study for. And in the next slide, I'm giving you like some real life documented like databases for those vulnerabilities. So probably like you have heard of that, and this is called like CVEs, common vulnerabilities and exposures. So these are databases like maintained by Mitra, like a non-profit organization sponsored by the US government. And these are completely publicized vulnerabilities. And alongside of each, probably you also come with like corresponding patches. Um, and well, so in the background, there are the columns shows you different forms of vulnerabilities, thereby categories. And you might think that, okay, vulnerabilities, there are so many, like, there are also like so many categories, but we can further categorize them into like actually like two main classes. So one is memory safety based, and the other more high level application level logic bugs. And the two main examples, they are input injection and broken access control. Um, so memory safety vulnerabilities, and we'll be like mostly focusing on them for today's session. And what are they? They are actually like they are like they are related to low-level memory management issues, and mostly they exist in languages such as C and C++, due to like some improper direct manipulation of the machine memory. And examples, so from the background, the columns, they are actually the first two, buffer overflow and memory corruption. So we'll be talking about this like in the future, in the later slides, but these categories, they are also like non-exhausted, and many other memory safety vulnerabilities you can think of probably are used after freeze, and just dangling pointers, double freeze, etc. Um, so why we specifically focus on memory safety-based vulnerabilities? A practical evidence here is that around 70% of critical security bugs reported by those like big tech companies, Microsoft, Google's Chromium, or Ubuntu Android, they are all memory safety related. And even that, your daily interacted like OS, mainstream OS, the Unix, Linux, macOS, they are all like written in memory unsafe languages such as C and C++. Or you might think of like language, probably like there are memory safer languages such as Python, but the runtimes of these languages, they are still like written in C and C++. Or the web browsers you're using every day, like for example, the JavaScript, they are still like running, the V8 engine is still like written in C and C++. So, while the critical infrastructures that you interact daily, they are kind of trusted, meaning that you place full trust on the system without actually knowing that there are actual protections there. Um, and memory safety vulnerabilities, they are the first, the top one critical zero-day vulnerabilities that can cost governments and institutions hundreds and millions of dollars. So let's answer the question, why memory safety vulnerabilities mostly occur in C and C++, but not other languages. And the key distinction between these families of languages are that memory safer languages such as Java, Python, they have the runtime to automatically manage memory for you. So you don't have to so there are like mechanisms such as garbage collectors or compilers, bounce checking, they're already like doing everything for you. But for C and C++, you have to like manually allocate and free those memories via pointers yourself. Um, and pointers, are dangerous to use, and they're specifically designed to give programmers flexibility to manipulate system resources, and they are purposefully designed for speed in processing, but they come with the cost in security. And the other key distinction there is that the specification for the C family languages purposefully leaves blank for certain behaviors. And that means that the compilers for those languages, they they actually compile some undefined behaviors without giving warnings for you or stops the program. So when your program runs, it could lead to like some haphazard runtime crashes. And this makes you like these are not easily traceable. So you might be wondering like why your program crashed without knowing the actual reason. But for those like runtime managed languages, they often have like much stricter like semantics, and well they also follow the semantics themselves leaves very few escape hatches, and those hacks are will be like giving like developers very restricted control so developers will be warned that if they use those escape hacks they will be like needing like extra concerns for those code. Yeah.
So
So
can I just jump in really quickly? Sorry to interrupt. We've had two questions on this, and I think it would be interesting to just get the answer. So we're talking about C and C++. We have two questions asking, is C sharp considered memory unsafe as well?
I think C sharp is a so I haven't used C sharp before, but
Mm,
based on my knowledge, is actually a object-oriented language, and
mm,
so if it has a runtime, then it should be like more memory safe. Yeah,
yeah,
it is.
yeah,
It is. I think it is memory safer. Yeah. So
yeah.
if it is like vulnerable, then of course it falls under like the C family languages. But I
Mm,
think my C sharp is used by Microsoft.
yeah,
Yes.
that's right.
Yeah, that's more like memory safe. Yeah.
Thank you.
Okay. So we mentioned about pointers. Well, if you are unfamiliar with pointers, they are basically like some um, first class members that store memory addresses of other language constructs. So they are dangerous to use because architecturally there are no rules built in to distinguish it like from memory addresses. Yet they are dynamic and powerful. That means they represent software's ability to access hardware and system resources. And this could be like reading and writing to memory. Um, so, well, so if you misusing them, of course you can corrupt or leak memory. And the two main sources of memory safety vulnerabilities are, well, spatially, you could have out-of-bound access or buffer overflow, and temporally, you could have use after free. So a more in-depth explanation for this is that, well, pointers are always associated with a dedicated region of memory, or we say buffers. And since they are treated as integers architecturally, they move by conventional arithmetic. So if we move them outside their allocated region, and we try to access those mismatched region, well, it could actually cause like spatial memory safety errors, like buffer overflow or out-of-bound access. And specifically, when we write to it, it is called buffer overflow. And temporally, well, when we free a region of memory and later access that region with the old pointer, and it could be a problem because now that pointer points to a memory that doesn't belong to it. So it could cause memory leaks or invalid access, and well, you can corrupt that region of memory, so it's memory unsafe as well. So if we already like understand why memory safety vulnerabilities could occur in C and C++, I want to show you some like real demo with yeah using like some we can hack some C program yeah using very common attack method. So the key attack vector we are using here is return-oriented programming. And this is a attack that tries to corrupt the function return address. It tries to change the original program control flow to point to some attacker-controlled code. And it succeeds by exploiting existing sequences of instructions that are already present in program memory. Either it could be in the source code that you write, or it could be like in some shared libraries such as libc. So here is a very simple program that contains some vulnerabilities. And so here is a main function entry point, and it can take more than one argument. And if it takes more than one argument, it calls function one with the second argument as input, and print, and then it returns from function one and prints hello world. And what function one does is it allocates a buffer of 16 bytes on the stack, and it calls the string copy function, which is provided by libc. And well, it copies the input string to the buffer and returns. And function two here is unused, but inside it, it prints hello from function two, and then it spawns a new shell process. So just want to ask you the question, do you see any like exploitable gadgets there to achieve the return-oriented programming attack?
Yeah, so we've got a poll for this. So do feel free to have a go at answering this. So what we're looking for is which sort of bits of the code there do you think are vulnerable, or can you see anything that an attacker might be able to exploit? Maybe thinking back to some of the things that we've mentioned. Um, if you have absolutely no clue whatsoever, absolutely fine. That's absolutely fine. Just submit a blank answer, and that way I will just know that I will know not to wait on you because you're still typing. So if you're not sure, just submit a blank answer. But we will wait for those of you who are still typing. I'll give you about 30 more seconds. So yeah, do have a think. But we'll try and move on fairly quickly. And we'll go through this, of course. So while we're waiting for some answers, there was quite an interesting question in the Q&A I thought I might ask, which is, can pointers destroy a computer by writing over vital memory? So things like startup sequences, or is this not something that's possible?
Uh, so the hardware will have like a number of mechanisms to stop you from just directly overwriting those very critical kernel code or the bootloader code. So actually we have regions of memory that are read only. So that's the design that specifically stops you from doing that.
Amazing. Thank you so much. All right, so what I'll do now is I will close the poll. So if you are still typing, please try and submit in the next 5 seconds. So I'll just close the poll now. Thank you so much to everyone who submitted. And we'll have a quick look at the results. Um, yep. So I can see lots of you, lots of you have got it. So someone has pointed out that the system /bin/sh, so the call to the shell is potentially dangerous. So quite a few have got that one, and quite a few of you also have picked out the buffer, sort of the sort of array that we have there. So that's yeah, great work. Thank you to everyone who submitted.
Okay, so yeah, definitely the system being shell that function call is dangerous because well it's it could so it spawns a new shell process that actually allows you to interact with the operating system through any valid system call. So well it could be like use of a gadget. But for the attack vector here, yeah, to be more specific, well, buffer, of course, it is very suspicious, but the exact vulnerable place here is the string copy function provided by libc. So it is by design on memory unsafe. The compiler doesn't check the length of the buffer and the length of the string input, the s. So it allows well very dangerous overwriting the buffer like even after the allocated region. So it could result in potentially like buffer overflow. So I have a simple exploit script actually taking advantage of the last two vulnerable places that the lines that yeah the program contains. So this exploit script uses a library that allows us to automate this exploitation process. So it automatically finds the gadgets and the goal here is that we want to craft an overflow payload and to override the return address of function one and direct the program's control flow to function two. Um, so here we craft the overflow payload and we are mimicking ourselves as the attacker here, and we start the vulnerable program and we inject that overflow payload and we attach an interactive terminal to the process to see that how far our attack can go. Well, so before we see the attack outcome, um, so I want us to understand the program, the where the vulnerabilities are from an architectural stand of point of view. Um, so this assembly is so this is through like disassembly. Well, disassembly is a concept in reverse engineering. And this is specifically a step to reverse what the assembler does. So it turns a final executable or binary into the assembly code. These are like a sequence of instructions that will be interpreted by your hardware. So we will be like seeing a number of instructions in our in the final disassembly output, and we'll be like understanding where the vulnerabilities are from a architectural point of view. Yeah. So here is the disassembly for the vulnerable program. The key point to note here is that well, for each function call, we have a prologue and epilogue, and on the prologue, and to understand the raw attack better, we only need to understand what the function call does, like during the prologue and epilogue, because we are only interested in the return address. Um, well, that's contained in the link register, and link register by convention. Well, this is in our ARM64 architecture. It is represented by X30 register. So on the function prologue, we'll be like pushing a number of registers on the stack, including the link register. And on function return, we'll load back that link register, and we will read the address contained in the link register, and then we'll jump to that address on function exit. So by pure inspection of this assembly, where well each line consists of memory location and memory location. After the memory location, you have the offset, and then it's the actual instruction. And each instruction, well, you have the actual action for that instruction is the instruction mnemonic and a number of different addressing modes. Well, so if you are familiar with this instruction set, you'll be you'll be like very shocked that there's no actual protection from the hardware. That if you change the return address in X30, the the hardware will just interpret it and decode and just do whatever you instruct it to do and branch into that value there without any checks for what that value is. So this is very potential for the rope attack. And the bad consequence would be like remote code execution. So this is the attacker's ability to run malicious code on the target system or process, as long as he's connected over a network. The worst case is just that you branch to some source codes that are controlled or memory location that are completely controlled by the attacker. So this could result in arbitrary code execution or complete system takeover. So it's just a proof of concept. We're not actually showing remote code execution, but we are mimicking that in a local process. So when we run the exploit script, um, the Python library finds us the exploit chain, and that exploit chain shows the memory location, the exact memory location for function 2, and it calls that function. So this is the exploit we want to achieve. So running the exploit program, and we are inputting that exploit overflow payload into the vulnerable program. And here you can actually see we are invoking the print function from func2, and we are still like remaining inside the attached terminal. So we can just try running any like syscall like to the terminal. For example, we are running like list here. So the software program doesn't stop you from doing that. So you're still maintaining inside the terminal. That means you can run any syscall as you wish. So the system, the software, at least this program is being undermined. So now let's shift our attention and to the hardware and software interface part. Well, what do you think this interface is, and in what ways do you think it could make it is related to software security, and how do you think it could make the software system more secure?
Yeah, so I've just launched that poll. So we've got those questions up in the poll. So do have a go at answering them. So what do you think the hardware software interface is? And then the second question is, in what ways do you think that a hardware software interface could make software systems more secure? So because we've got two questions, um, I'll give you a few minutes to have a think about that. And don't worry if you're not sure. Um, do give it a go. Um, and we'll have a look at the answers in a few minutes, like I said. So if it helps, because we haven't had many answers. If it helps, if anyone's struggling with the first question about the hardware software interface, it might be worth thinking about one of the seminars that we had quite a few weeks ago now about abstraction and thinking about sort of the layers that make up a computer system and thinking about where you might place the sort of the hardware software interface in between those layers. Have a think about that. Yeah, thank you for everyone who has answered. We've only had about 30% of you answer, so I will give everyone another minute just to have a think. Um, if you do have absolutely no clue whatsoever, do feel free to just submit a blank answer, and then that way I just know not to wait for you. Um, so there's quite an interesting question in the Q&A. So while we're waiting, I thought I'd just ask this. So is there a way of fully avoiding attack um, through sort of writing better code, or will hackers always find a weakness to exploit? What do you think?
Well, that's actually the main point why we are researching this hardware assisted yes for software safety because we'll actually be addressing this question later because it's kind of the exact reason why software um only protections are not enough. Yep.
Great. Yeah, thank you. So we'll circle back to that. But yeah, if you do after we've gone through it still have another question, feel free to sort of follow up with that. So I will just move on now. So thank you to everyone who has submitted. If you are literally just finishing the last few words, please submit that in the next 10 seconds, because that's when I will close the poll. Great. So like I said, thank you so much to everyone who gave an answer. I'm just closing the poll now and have a quick look at the results now. Um, Great. So we've got lots of good answers for the first questions. So, for example, someone says the way that the software instructions are translated for the hardware so that it can execute those instructions, something that sits in between the hardware and software and lets the software interact or communicate with the hardware. Um, loads of great, loads of great answers. Somebody has said. How the software is able to interact with the hardware while hiding the sort of exact specifics, which is great because that links exactly to the talk that we had about abstraction and how we can sort of abstract away detail. So that's perfect. Yeah, lots of brilliant answers for that one. And then for the second question, in what ways do you think the hardware software interface could make software systems more secure? You've got, again, lots of good answers. Somebody has said it can protect memory. Um, it will be able to use validation to make sure that software, um, if software tries to do something damaging, it can prevent that. Um, it can verify a user. Access controls. Loads of loads of great answers on that. Um, yeah, amazing. Thank you so much to everyone who gave an answer. And yeah, we'll move on now.
Yes, yeah, thank you so much for giving the great answers. So for the first question, many of you actually give, I think, very precise definitions for what this interface is. But for the second question, we'll see later. It's actually related to how you design new instructions and how you design like real corresponding components in the microarchitecture to achieve that, and how software makes uses of those hardware provided features. And you have to purposefully enable that for the software systems to actually take advantage of that protections. Yep. So let's continue. So yeah, so I've given you like the abstract abstract layers for the computer stack, and the interface just sits in between the software side and the hardware side of stack. So, well, probably you have already listened for have sat for that session where you discuss those different layers. Well, software just consists of like applications on the top, underneath, well, you're always written in some form of like programming languages. It could be compiled, or it could have a runtime to manage everything for you. And underneath that, there's an operating system that translates your requests to the hardware, and yeah, just gives you response. Um, and the interface is just the instruction set architecture, which defines, yeah, how software communicates to the hardware. And the hardware actually includes the hardware resources includes the CPU, the memory, and many other peripherals, such as your monitor, your mouse, or something. Yeah. Um, so in formal definition, this instruction set architecture is defines the set of instructions, data types, registers, and memory models that your CPU understands. So why do we revisit this interface for software security? Um, what is actually missing in the current security landscape? So, well, the fact is that currently we have most of the mitigations only like software based, and of course they are very incomplete in their coverage. So we have, you might heard of like, well, compilers, they have static inspection, and we ha also have like runtime sanitizers. It could be like memory sanitizers, address sanitizers, and they have like some fast inputs to explore the edge cases in your program. And well, like for those like disclosed vulnerabilities, and you always have like patches to mitigate those impacts. But these exploits and patches, they're always in an arms race, so never stop. So what we desire instead is we want some deterministic protection for those known classes of vulnerabilities, and even like for vulnerabilities that we don't know yet, we still want to mitigate them by confining impacts within those undermined or compromised regions.
Yeah, sorry to jump in, but somebody's asked quite a good question, and it is basically they're asking which part of the sort of stack that we were looking at is the instruction set architecture a part of? Um, yeah, where does it sit? Oh, it's on here. There we go. So this person has asked, is it part of the operating system? Like, what is it a part of?
Nope. So it is a abstract layer on its own. So it actually doesn't belong to any of like this concrete layers. So it's actually like a specification that defines it gives you it sets out a number of instructions that hardware will implement, and so software can uses that instructions to instruct hardware to do anything like for them. And so yeah, microarchitecture is the implementation of the those instructions that hardware implements. And yep, so that's basically a set of instructions with registers, um, exceptions, and like those memory models. Well, those are very abstract things, not physically implemented. Physical implementations
Hmm.
are just like microarchitecture. Yeah.
Great, that's perfect. Thank you so much.
Yep. So let's continue. Yeah. So the big idea for, well, including this interface in security design is that we want to build these new security primitives into the architecture. Well, be it machine understandable instructions, registers, data types, memory models, such that we can provide software those guarantees from the very bottom of the stack. And to understand how to build security into the interface, we might need to understand what are the mainstream ISA design philosophies. So there are two. One is CISC and the other is RISC. So the key distinction is that CISC instruction relies very heavily on the decoder to do things for you, while the instructions are variable length, so they are much harder to decode. The RISC, on the other hand, they are fixed length instructions, and the very prominent example of those instructions is the memory access model, where in CISC you can directly operate with memory so in your instruction, but in one instruction. So the instructions length is variable. So you have like very lengthy instruction there. So it's this example is a x86 instruction. And on the right, we have um, the load store architecture. That means RISC. When you want to operate values stored in the memory, you have to explicitly load them from the memory and put that into the register. And there you can do any kind of operations you want, be it arithmetic or others. And then if you want your results to be persistent, you have to store or probably not persistent, but you have side effects. You have to store your results into that memory address again. Um, but for the mainstream, the mainstream architectures now it is more favor. They are more so the tech companies they favor risk more because we this place much less burden on the microarchitecture design. So we have like um yeah much simpler decoder logic. So this means we can tape out new chips more frequently for experiments. Yeah. So um well, the point here is that I want to show you some real risk ISA with security built-in. So the example here is through ARM pointer authentication extension. So this extension consists of a number of new instructions, starting with pack and auth, and they are used inside the function prologue and epilogue. Um, so, well, what this does is they actually counteract the ROP attack that we had before. So we'll be showing the exam vulnerable program and compiled with this ARM pointer authentication extension, and we'll show you that the vulnerable program is actually caught and stopped and yeah, so we cannot launch any ROP attack anymore. So how this pointer authentication extension works is on function call. So we save the return address, but so before we saving that saving that value on the stack, we actually ask the CPU to sign with some cryptographic hash function using a hardware known secret key and the current context like the stack pointer. And on function return, we ask the CPU to verify the signature such that it is not manipulated, it is not its integrity is maintained. And if authentication fails, the CPU will automatically generate a hardware exception and the OS will check the application so such that there's no ROB attack. So yeah, show you the disassembly. We recompiled with this extension. Um, so clearly in the same function disassembly. So on the top, you see the new pack instruction, and on the function return, you see a new return instruction. So the pack instruction there um, stands for pointer authentication code for instruction address using key A with stack pointer modifier. and exactly doing what I described before. And the return address stands for return from subroutine with pointer authentication using key A. Also, authenticating the address in the link register before doing the branching. So we run the exploit on the recompiled program, and instead of invoking the print function in func2, we've actually got an EOF. Um, and when we doing the same list syscall, well, the architecture just gives you some sig fault error, zigzag fault, and well, we're just thrown out of the terminal. So no more rope attack. So well, this is a direct proof that we can build security into the interface, and the interface is actually working for our software applications. Yeah, in terms of security, better security. So apart from the pointer authentication, so just as more complete information, there are also many other security extensions, and each is designed with very different approach. For example, ARM-MT, it adds new instructions for runtime memory access, and on the other hand, Cherry, so the capability works by directly changing the pointer type in the architecture and changing its layout in memory by adding security metadata alongside it. So the point here, so I'm not going to into detail for these mechanisms, but the point here is that the design space for adding security into the architecture and that hardware software interface is quite large. And each microarchitecture can have the choice to implement any extension they want. So, a last question. Um,
Yeah, so I might just jump in here and just because we don't have very much time, I
okay.
might suggest that we skip this question and
Okay.
actually answer some of the questions in the chat because I think they're really
Okay, cool.
interesting
Okay.
and it might lead to quite an interesting discussion. So one of the questions that's on here is so we've spoken a lot about, C and C++ and how they're memory unsafe. And somebody's asked, why are C and C++ so widely used despite being so much more vulnerable to these memory safety related attacks compared to other languages?
So, well, it's a long history. So, well, when people are writing operating system, um, so it's actually like dating back to last century where C and C++ emerged first, and then they are actually a high level wrappers for the assembly code, and assembly are just like those instructions listed inside this instruction set architecture. So C and C++, they are designed without the security in mind. So well, they are just designed for speed, so the priority there was to have like so we can so our so we as developers we can instruct the hardware to do things at very high speed for us, and that's the first priority for those languages. But yeah, so later we find out, okay, memory safety is quite costly, and then we kind of want to, well, think of like if we can incorporate some mechanisms in the more higher level languages, such as like Python. So they have like runtimes, so managing like some of this memory management for us. Um, but like those operating systems, they are written like in the old days, the very early days, and at that time, well, those are legacy. So those softwares code bases are kind of like legacy code bases nowadays. So in the security like landscape, we are also thinking about if we can rewrite those memory unsafe um, infrastructure in memory safer languages, but those are not very practical approaches. Yeah, so well, this that we are left with this conundrum. So, well,
Mm, mm,
no
absolutely.
choice.
Yeah. Thank you so much. And another question which I thought, I'm sorry, I'm slightly taking over because I know we only have 5 minutes, and I think these questions are really interesting. So if you're happy for me to, I will keep asking some more questions from the chat. Is that all
Oh,
right?
yes, sure. Yeah.
Great. So one of the things that we spoke about was how, of course, we've got these vulnerabilities in C and C++, and somebody's asked if you think that with people using AI to write code, do you think this will mean that there's a higher sort of incidence of these types of vulnerabilities happening? Because, for example, the AI will give you code that's vulnerable? Or do you think that's something that's considered by these sort of AI systems so that they make sure they give you good code?
Well, so it really depends on which language you ask the AI to write in.
Mm,
So as I said, so if you ask the AI to write in C and C++, then definitely there's a chance that they don't consider like security because we don't know like what kind of like data like these models are trained, right? So
mm,
I definitely like recommend more caution when using like AI for writing like C and C++ code, but definitely I also um I have some confidence in the current like hardware provided features, the protection features. So mostly, um, some are caught by compilers, some are caught by the hardware. But of course, like if you understand what the code is doing, then that's better. Yeah.
mm. Definitely. All right, I will let you maybe try and sort of
Yeah, yeah,
finish
yeah,
up
yeah,
in the
yeah.
last few minutes.
So yeah,
Great.
so I just want to highlight that some common aspects among those hardware's security extensions is that they share the same design approach. So this is by co-design, hardware software semantics. So we always start from designing new instructions, and we are ensuring that there's no overlaps in the encodings, and then we design some decoder logic, data path registers onto microarchitecture, and we want to verify if the new instructions break the existing functions of the chip, and then we tape out, and then we try to adapt our software stack to make use of the hardware provided features, and then yeah, we benchmark the software systems and look. This is a development cycle, and we look back to the beginning to optimize the design. And another thing that they share in common is that software system must deliberately like enable these hardware features um, to make use of the so we also have a number of scope that we can add the protection for. From the kernel space, the operating system, we can enable that like from the bootloader, or if you want like system-wide protection, even like protect from the start of the device, then we can enable that like through some shared config files or environment variables, or if like through benchmarking, we find that the runtime overhead for software system is too large, well, yeah, then you can optionally enable that, like just for a single application at runtime. And that's through like some compiler flags or allocator tunables. Yeah. And the last but not least, definitely we have some design trade-offs. From software perspective, like when turning that hardware protection on, like how much overhead will there be, like for in terms of execution time or memory footprint, or how much change is needed to use that hardware feature in the ecosystem. And by ecosystem, we mean like libraries or tool chains, or break you, does that break the existing functionality of this software? And in terms of security, how much improvements does this feature actually give? Is it deterministic guarantee for some classes of vulnerabilities, or is it just probabilistic? And in terms of the hardware, how much more area and power is needed? Does it slow down the number of operations that the CPU can process per second? Well, those are the very valid concerns when you design these new architecture features. Yeah. So if you want to read more, so actually this is a multidisciplinary research. So I've given you like some undergrad level introduction um, to computer architecture, systems, and security. So I hope you enjoyed that. Yeah.
Great.
Any
Thank
further
you so,
questions?
so much. Yeah, thank you so, so much for that talk. We are running out of memory, but we will take maybe one or two more questions just because there are some good ones sort of waiting. And one of the questions is, can we just update the languages C and C++ so that they have more security in them?
Um, well, so the ISO spec itself is memory unsafe by design. So I I don't think the community will agree that we add like this security like inside these languages because these languages are designed for speed. So if you want to add like memory safety as like a first class concern, I don't think so it kind of like violates the like the intention of having these languages first. Um,
Mm-mm-mm.
but if you want speed and more like safety, you can actually turn to Rust. So that's a new newer language, but it is also memory safe. Um, but there's also like some caveats in that. So it's a
Mm-mm.
very active research area. So yeah.
Absolutely. And then one question that's also been asked, and I'm not sure, I guess I'd be interested to hear your views on this. Um, and it is, what role do you think AI plays in cybersecurity?
Um, well, that's a great question. It really depends what how you're using the AI for. Because I think if you are using AI for improving security, then definitely you have to retrain the model like from the beginning. So you have to. So I don't know if there's are any like existing models that are designed for this. Um, but yep. So I only know that like the current AI models are mainly used for like general purpose like chats or
Mm,
so more utility based instead of like for security.
mm. Do you think that there is like a research interest in this area, or is
Yeah,
it something that's
definitely.
not really been explored yet?
Um, so definitely there will be like interest in doing this because I have heard like um some there are like plans to using AI to yeah just translate, like rewrite the operating systems into like
Mm,
Rust or something. But
mm,
that's also like error pro, error prone.
hmm.
Yeah, so not sure like how far that could go. And
Yeah, yeah, yeah.
especially I'm actually like associated with the Cherry group, so we are kind of like suspicious of that approach.
Absolutely.
Yeah.
And then we are just out of time, but just one thing I wanted to do quickly is somebody asked if they could just have a look at the slide with the books,
Okay.
just so they could see the titles of the books again. So that's great. Thank you so much. But yeah, I think we'll unfortunately have to finish up there. Thank you so, so much, everyone, for coming along. And then just a quick reminder that on Thursday we're going to have another seminar. So that one will be on large language models. So it's happening on a Thursday because we had to cancel it, unfortunately, a few weeks ago. If you can make it along to that one, please do. You should just get a Zoom invite as normal, just sent straight to your email. Another quick reminder that next week we have the admissions talk. So that will be on our regular sort of Tuesday slot. So if you're interested, please come along to that. You will have to sign up to that separately. I will send a link. I'll send that link in a few days' time, along with the recording of this session. And then finally, when I finish this webinar, you will have a feedback survey pop up on your screen. Please, please, please do fill in that survey because it's really, really helpful to me to hear what you thought. And I won't keep you any longer. Thank you so much, everyone, and have a good rest of your evening. All right, bye.